In this figure, we'll talk about the limitations of diffusion and how they are a driving force for the evolution of organ systems and actually help us explain many of the anatomical or physiological characteristics of those organ systems. Let's start at the upper right here with a very simple equation for diffusion. This is the Fick equation. J diff, or the diffusive flux, the rate of diffusion, equals the diffusion coefficient times the surface area over which that diffusion is occurring times the concentration gradient, gradients drive diffusion, and is inversely proportional to, on the bottom of the fraction here, the distance over which that diffusion is occurring. Now these hopefully make good sense, right? If we have greater surface area, we should be able to have faster diffusion. If we have a larger gradient, that drives faster diffusion. If we have a smaller distance, we should have faster diffusion. Again, inversely proportional. And so what we find here is that distance is a very important component of the limitations for diffusion. In addition, the surface area as well will be one of the factors that is altered when we transition from unicellular to multicellular organisms. So in A here, let's look at a unicellular organism. We're going to give it an arbitrary radius of 1. Now let's start first and say, well, if we're going to diffuse something from inside to outside this cell, or vice versa, the distance over which that diffusion must occur is actually quite small. And of course, that distance is small, then our rate of diffusion can be very high. That's good. In addition, we find that using this radius of 1, and if we calculate using geometry, the surface area and the volume, and then the ratio, surface area to volume ratio, this is actually going to be a relatively high value. The smaller the organism becomes, the higher the surface area to volume ratio is. This means that there is greater amount of surface exchange area with the environment in smaller organisms, also advantageous. Now, during the evolution of multicellularity, we've got a multicellular organism down here in B, we're going to give it an arbitrary radius of 10. Well, first thing we see is that cells in the deep interior must overcome a much larger delta X distance to diffuse substances into and out of that particular cell. That is going to dramatically delay that diffusion, make it slower. In fact, we can actually give you a very simple equation for the time for diffusion. Time for diffusion is proportional to delta X, the distance, squared. And what that means, this exponent is really important because that means the time for diffusion goes up very dramatically as distance rises. Again, because of this exponent, it's an exponential relationship. And so we want very small distances to have very rapid diffusion. That's, of course, not the scenario down here in our multicellular organism. Strike one, right? That's bad. Additionally, if we calculate the surface area to volume ratio, again, just using the geometry of our sphere here, we end up with a much smaller value. We went from 3 in our unicellular organism to 0.3. This means there's less surface area per cell for exchange with the environment. How do we overcome this? Well, this limitation made it such that without any adaptations, these organisms, multicellular organisms, couldn't get any larger, right? Diffusion was just too limiting. And so that was a driving force for evolution of organ systems that allowed for much more rapid transition of substances to and from cardiovascular system, or dramatically increase the surface area of the organism for exchange with the environment. Think about the very large surface area of the lungs, or microvilli in the GI tract, dramatically increasing the surface area to move nutrients more dramatically and rapidly into the body. The same is true in the urinary tract, in our nephrons of our kidneys, where we also have microvilli that enhance that ability to exchange with the environment. And so many of our organ systems are adapted to overcome these limitations of diffusion and allow the development of multicellularity in our evolution.